Hello everyone, myself Faizan Beigh from Department of Electrical Engineering from IIT Delhi. Today I'm here to talk you regarding a topic titled as optimizing strategies for laser-induced graphene on various substrate for flexible strain sensing. As you earlier saw the presentation of Professor, he talked about this flexible sensors, creating these sensors, and their process was quite complex. So in order to show some way that we can create some similar sensors, but with very simple method. So this will be the flow of my presentation. First, I will talk about graphene, why graphene is so important. Then we will see method of creating this porous graphene, that is also known as laser-induced graphene. Then we see some work that people have done in this field and some research gaps that are really needed to be covered right now in order to get some optimized results. And finally, we will conclude our presentation with some confirmation and initial characterization. So all of us know that graphene is basically a single atomic layer of graphite, and it's abundantly available, and it's highly usable. With this discovery in 2004, people begin to use graphene for various applications, like for creating graphene-based residue sensors, like flexible sensors and graphene electrode as well. But this was only possible when they came to know about its attractive properties like high mechanical strength, its Young's modulus is very high, as well as it's highly flexible with high optical transparency. And with having all these properties all together in a single material, they came to known as graphene as a wonder material. And if we look at the current scenario of creating this graphene, there are various methods of creating graphene. Like you can go for a liquid phase method, you can go for mechanical exfoliation, or you can go for CVD method, or you can synthesize using flash Joule method. But problem with all these methods is they have some issues that need to be addressed. Like in mechanical exfoliation, what you do, you generally have a graphite and you peel off a layer by layer in order to create a thin film of graphene. But problem is that, is this a way to create a graphene in a large quantity? No. And to have other ways of creating graphene is CVD method. But issue with this CVD method is that the instrument cost is very high, and some labs apart from India are very complex to create these type of graphene. So what is the solution to create this type of graphene? With Professor Tor from Rice University, he introduced us to laser-induced graphene, where he used the polymer sheet on which laser was induced, due to which a localized heating happens, and due to this, the sp2 hybridization of carbon start losing to sp2, and aromatic chains of graphene-like material start creating. And during this process, some of the gases and some bonds of oxygen and nitrogen start losing. And we saw that the rapid use of laser-induced graphene in the field of flexible sensors. But the problem is that, like in this work, you can see that they have tried different types of materials to create the laser-induced graphene. But issue is that the property that they use for this creating graphene setting is similar. And this has led to overpower issues, like in SAM image, you can find that graphene is missing. And similarly, you can see that they have created graphene on polymer sheets, but at the same time, they have casted some cement over it, and the effect of cement on the formation of the graphene is not being seen there. Because of this, they have lost their sensitivity, and their sensitivity is only limited to 100 to 100 ppm. But if they have to sense below this 100 ppm value, what they can do is they have to figure out this material that they have lost over it. And another way of creating graphene in this way, they use some natural materials like cork was used. But again, you can see the overpower use here. You have an unstable graphene. And similarly, they have created a graphene on Kevlar. And Kevlar is highly carbon content, and it's also used for graphene creation. But problem with here is that the poor response will always be existing because the effect of skin is not being considered. So all these work that I have shown here have problem is that their settings have not been quantified, plus their effect have not been considered of their substrate that have been used around them. So the only solution is that you will go for the optimization of all these settings. So before we will move towards there, so this is the machine that we have used. This is a low-cost machine. It cost around 3 lakh rupees to us. And this machine is not being actually used for creating graphene, but with our optimized studies, we came up with a way to create graphene. So this is throughout the work, we will going to use laser power as percent power, while as laser laser speed will be defined as scan speed, while dot per inch will be defined as DPI. and the energy per unit will be defined as EPU. And so this is a research gap. There is a lack of unified optimization approach for creation of laser-induced graphene. And if there are some different applications, like someone wants to create a gas sensor, so what should be the porosity of the graphene? Should it be high, low, or it should be highly conductive, or it should be highly resistive? So those things need to be quantified. Like these are the main parameters that we will talk about. So this is something that I created in my first year of PhD. I saw that creating a strain sensor required a clean room access. I used a photoresist, then I used a metal deposit over it, then some graphene nanocomposite deposition was required. This is a highly costly method, but to surprise us, we created a similar pattern using the laser-induced graphene with a single step and a rapid design formation. So this is the effect of laser power and the scanning speed. You can clearly see that good patterns are related to good LIG conductivity, and it was related by the thickness of the graphene that was grown with it. But it does not continue with that you will start increasing power continuously to up to any level. There is a limit that you need to control those both together. So you can see clearly at higher speed and lower power, the graphene formation will never be formed. Only you will get a lighter pattern with lesser conductivity. So the optimal range for our work, initially we found that 100 is the power, 100 is the speed, 100 meter per second, while its power is 20% of the machine that we have used. And these are the clear patterns that we have created using this optimized scheme. But we didn't stop it here. Our effect is the DPI. If you have to create an image, what will you look for? You will look for higher DPI. But in case of laser, this is not the case. In laser, your spots are something that will affect. So the distance between the spots is something that you need to be carefully managed. So what we found that if you increase this gap distance between the 2 points, there will be overlap. And due to this overlap, overpower issue will happen. And that we found in the previous work that their DPI was very high, due to which their resistance were very high. And eventually they lose the conductivity thing that we're targeting upon. And this is a clear violation, which we also try to simulate similar. Like we used the DPI of 350 at that time, our resistance came up to be in a kilo ohm, while for a DPI 256, it came to be very small resistance. Now, after this, we wanted to quantify all those things together, like speed, power, because some of might have a different this laser power in their machines. Like in our case, we were using 100 watts. So some might was using 20 watts only the power machine. So what they can do is they can control this ratio DPI and scanning speed. So you can clearly see that this range 40 to 60 is defining as the optimal range. And if your DPI is, if your energy per unit area is in this range, your sensors will be always having high conductivity. But again, for this highly resistive sensors, like you want a piezoresistive sensor, then you would go for this range of the sensors. And the confirmation was confirmed by this, we went for this Raman, and Raman showed us D and G bands. And D is clearly shown here a defect, while G is for sp2 hybridization scheme that we generally form with the carbon, and 2D is for the thickness. So the ratio of D by G should be smaller for higher conductivity. That is clearly seen for the optimal scheme, that is 0.035. And when you are increasing your overpowering it, what happens? Your ID by D ratio. This leads to fibrous graphene formation. And similarly, we did some XRD scheme as well, and we found that our dominant peak is at 25.9, that's clearly identified as 002 plane, and while fainter peak is at 47 degree. And then we did some SEM analysis as well in order to see the thickness of our graphene grown, and we clearly see that at higher power, your graphene growth is getting reduced, and it's actually becoming very thin, and it's losing the substrate adduction. And then this is again the similar thing that we talked about, this ID by D ratio. Beyond 45% of power, you are losing your material itself. And then we did some EDX analysis as well in order to find what is the change in the carbon content happening with each power iteration. So when laser power was 0, we found that carbon content is 72%, but your oxygen is 20% and your nitrogen is 7%. So with increasing power to 5% only and keeping the speed at an optimal range, we found that there is a small change in the carbon content. But with the optimal scheme, what we found that your nitrogen and oxygen is getting very small close to zero, and it means your higher carbon content is highly conductive. And the resistance increase due to the increase in the defect. That is again the concentration of higher power concentration. If you go for 30 to 45 scheme, you will find that your graphene formation is losing. So then we did some IEEE characteristics in order to see and we found that in nitrogen scheme that your resistance was around 375 ohms, and when there was a low vacuum, it changed to 364 ohms. It's very small, and the change is because of the moisture content loss when you increase the vacuum concentration. So this is the transfer mechanism. We try to figure out whether after transfer will the contact remain there. Yes, it remains there. It's quite clear after and before. We also use the PDMs for it. And after this, the conclusion is that we are not limited to only the flexible substrate like polyamides or these. We can go towards this green LIG as well with the use of optimizing scheme. Thank you, everyone.